Yes, let's settle down here. Hi everybody, Manjunath here. Welcome back to Daily Science Galaxy. As you recognized, I'm in the picturesque lap of nature. What a beautiful nature it is. A quote I'm reminded of, nature is always alongside. In the middle of nature, it's always great to be closer to the nature, gather your thoughts, relax with the family and friends. What better setting you could ask for in life, isn't it?
Hello, sir. Good morning.
Hey, good morning.
Great to see you in the park this morning.
Likewise here.
Sir, if you don't mind me asking a question, I need you to tell us a bit about hypothesis testing.
Sure, I'll tell you a thing or two about hypothesis testing.
What is a hypothesis? Can you briefly talk us about it, please?
Sure, I will. Let's do it. I've just moved under the shade to be able to tell you a little bit of details on the hypothesis testing. So first up, let us understand what an hypothesis really is. Hypothesis is something like a claim, a tentative claim, if you will, an assertion or an assumption, usually about a population parameter. And population parameter can be population mean or population standard deviation. For simplicity, I'm going to stick to explaining hypothesis testing in the context of population mean for comparison. So therefore, hypothesis is all about a tentative assumption or a claim or assertion about a population parameter. Let's say the salary of the population that you want to analyze. So therefore, hypothesis testing would be a structured approach to decision making and entails a framework to formulate an hypothesis. One is called null hypothesis and the other is alternate hypothesis. Null hypothesis is all about status quo. Alternate is complementary or mutually exclusive to null hypothesis. Simultaneously, you cannot have null and alternative hypothesis either true or, for that matter, they cannot be either false simultaneously. One of them is going to be true at any given time. And when you look at hypothesis testing in the context of decision-making framework, the onus squarely lies on the person who is willing to take the decision basis the hypothesis testing. The rejection of null hypothesis leads to what is called alternate hypothesis. So therefore, seldom in the real world, please remember this, you directly don't prove alternative hypothesis right. You prove alternative hypothesis right as a consequence of proving null hypothesis wrong. So when I say that, why do we even construct a null hypothesis, you would be wondering. So let me just explain. We construct a null hypothesis not with the objective, as I stated earlier, of proving the null hypothesis. We construct solely with the objective of disproving the null hypothesis, as a consequence of which we can go ahead with the alternative hypothesis. Typically, a decision maker would want to prove alternative hypothesis right, and therefore we would construct the null to disprove. Basis the evidence, if you have reason to believe null hypothesis, we can disprove, and therefore consequentially we can go with the alternative hypothesis. That's what the decision maker would want to do. Hope that helps you. Yeah?
Thanks for this additional tip, sir.
You're most welcome. There are a few more things I would want to add on that you must keep in mind when you formulate an hypothesis test. First thing is to say, null hypothesis, like I mentioned already, is about status quo, which means it always tests for equality. Never you should think of null hypothesis for testing inequality. You know what? Symbolically, even if you put less than or equal to or greater than or equal to in null hypothesis, it still tests for equality, because null hypothesis is like status quo. And coming to the alternate hypothesis, I've seen some people, maybe inadvertently, let's suppose, have made this mistake. In alternate hypothesis, you should not have equality sign, period. Alternative hypothesis is never about checking for equality. It's always testing the inequality in the alternate hypothesis. So what I mean by that, you could have symbolically less than in alternate, greater than in alternate, and unequal in alternate, and never put equality. So remember, Null hypothesis, just to summarize, is all about testing the equality, even if you put less than, greater than, for example. And the alternate is all about checking the inequality. You must never put equality sign in alternate. That's a wrong way of constructing or formulating the hypothesis testing. Hope that helps as an additional insight.
Sir, can I just go ahead and ask you another question?
Sure, please go ahead. I'm all ears.
How does one go about the choice of hypothesis testing?
That is yet another great question that you have asked. Thank you very much for asking that question. I really appreciate it. So before I answer that question, let me tell you something even more important to my mind. The choice of hypothesis testing is dictated never by null hypothesis. Remember, the choice of the hypothesis testing to be performed is dictated never by null hypothesis, but always by alternate hypothesis. So don't make the mistake of using null hypothesis to decide the choice of hypothesis testing. So it's always the alternate hypothesis that decides the choice of hypothesis testing that you perform. So coming to answering your question as to how does one go about looking at multiple hypotheses. Think of it this way. I'm going to talk just about 3 hypothesis tests. First, the t-test. Second, the z or the z-test. And the third, ANOVA, ANOVA, stands for analysis of variance. These are quite popular hypothesis testing that you perform from time to time in the context of decision making. Semantically, there are certain differences between when you apply what. I'm going to help you with some elaboration. Think of it this way. T-test is an hypothesis test. Z-test and ANOVA tests are also hypothesis tests. T-test you would typically use when you have the sample size that is small and standard deviation is unknown. And Z-test you would typically use when sample size is relatively speaking large and the population standard deviation is known. So the choice of looking at the tested statistic as in T or Z statistic depends on the sample size and the standard deviation of the population known or unknown. So between the two, t-test is very practical to apply because in a real world setting, oftentimes, seldom you would know the population standard deviation. So therefore, between t-test and z-test, t-test is more practical. The purpose of t-test and z-test is to compare means across 2 groups. So often it is used as pairwise comparison for comparing means of 2 groups. So hope you are clear with the distinction between t-test and z-test and also the purpose of t-test and z-test. So let me transition to explaining ANOVA briefly. ANOVA stands for analysis of variance. So a lot of people mistake we're actually measuring variance using ANOVA. It's in fact, using the ideas of variance, you're actually comparing the means of multiple groups. Multiple means how many? Like I mentioned, for t-test and z-test, you will have to have 2 groups for comparison of the means. Quite often that's the setting. For ANOVA is applicable where t-test and z-test are also applicable. Make no mistake. But ANOVA is a very elegant technique to compare the means across multiple groups. Multiple meaning more than 2. It could be 3, it could be 4, it could be 10. So wherever t-test and z-test have limitations, ANOVA triumphs in the sense wherever t-test and z-test are applicable, you could also apply ANOVA. But here is the twist. If I have, let's say, 4 groups and I want to compare means across these 4 groups, I have a choice to use t-test and z-test subjecting to the sample size and the standard deviation. But then here is the catch. When you perform for more than 4 groups, pairwise comparison of means across 2 groups, your type 1 error or significance level, we represent it as Greek symbol alpha, gets inflated. That's highly undesirable because it will have unintended consequences. So what you do when you want to simultaneously compare means across more than 2 groups, let's say 3 or 4 or 5 groups, you want to use elegant technique like ANOVA because simultaneously you can test for the hypothesis and it does not inflate the type 1 error. Type 1 error would be quite costly. If you inflate it, you're kind of almost inviting trouble. For ANOVA setting, what is the nature of y and what is the nature of x? So let me just explain. The nature of y should always be continuous. Like for example, salary, insurance claim, the nature of independent variables should always be qualitative or categorical. And independent variable in the ANOVA setting is also called factor, is also called treatment. In fact, ANOVA has its roots in terms of its application to an agricultural setting. That's why we call it as treatment, so to speak. So when I say independent variable has to be categorical or qualitative or treatment or factor, all means to suggest the same thing. So the Y has to be continuous and X has to be categorical. A good example is, let's say you're an insurance provider in a certain country and you provide insurance across 4 regions of a country. Let's call them as north, east, west and south. So a decision maker would want to evaluate if the average insurance claimed across these 4 regions of the country is similar or they're different between different regions. So it's a classic setting for doing hypothesis testing using ANOVA. Here, make no mistake, I could take rather 2 regions at a time and do pairwise t-test and z-test subjecting to criteria, but it is not an elegant way because it inflates the type 1 error. You should be mindful of not inflating type 1 error for decision making. In the context of ANOVA, the number of independent variables decide the nature of ANOVA setting. We call generally N-way ANOVA. N stands for the number of factors of the independent variables of the treatments themselves. So when N is equal to 1, we call it as one-way ANOVA. When N is equal to 2, we call it as two-way ANOVA. When I say one-way ANOVA, you can simplistically think of this as one factor or one treatment variable. When N is equal to 2, I'm referring to 2 independent variables and therefore 2 factors and therefore 2 treatment variables. So that's how you go about performing ANOVA testing. So I was mentioning about a good example. You can think of, for example, how is the average insurance claim across 4 regions of a country, north, west, south, east? Is it same across all the regions or different for different pairs of regions?
Thank you for the insightful response, sir.
Sure, you're welcome.